So I ended up. Right. Luckily, it was like right after. So I had that. Yeah. Yeah, that's safe. When you got this tattoo with the sure. Yeah. But I designed it myself. Like I came in having drawn this out already. Did they ask you? Yeah, sure. My brother, they grew up at it was important that they were like very precise and specific. I pitched this to my brother first because I didn't want to that good vision. Oh yeah. Got a lot. So he immediately goes into no, that's literally not the point. Literally not the opposite of the point. So I didn't want to like that. Again, yeah, it's like a really
If you ever forget why you don't do math,
that was the thought.
Hi, welcome back for the last talk of today. A couple of announcements before. So regarding the banquet, if you intend to bring a guest, if you have not yet paid, or if you are on the wait list and are still interested in going, go to the registration table right after this talk and we'll get you all settled. Also, if you are kind of like looking for a group to kind of travel with, there's going to be a cluster forming with Rami. He is now standing up in the back. So find him after the talk for information about that. The next thing is tomorrow, because things are exciting, we are not going to be in the CERC lobby where all the tables have been. There is another event that's going to be happening simultaneously. So if you see people that you didn't see today, they might, I don't know if they're going to be wearing this. Sorry. Okay, so we don't know what the event is essentially what's going on. So just be aware that there might be a little more confusion. So there is a lobby on this side of all of the rooms, and that's where we're going to be tomorrow morning. We will have signs. You'll come in the same entrance. You'll just have to filter past them to get to us. So yeah, so that's the thing. All right, so our speaker now is Priyam Patel. She got her PhD at Rutgers University, working under Penguo, and is now at the University of California, Santa Barbara. And today she's going to be talking to us about mapping clusters of infinite type surfaces and their action on hyperbolic graphs.
Okay, thank you. Thank you to the organizers for the invitation. Please do let me know if I'm not writing big enough. Like I usually tend to start writing smaller, so if you can't see it, just let me know. Okay, so try not to get distracted by the beautiful pictures that I've drawn up above for a second. Everything I'm going to talk about today, well, really it's stuff that I'll get to towards the end about these actions on hyperbolic complexes. It's joint work with Carolyn Abbott and Nick Miller, and it's preliminary work. We are still writing the paper, but I promise the things I'm telling you are true. Okay, so we'll start off with today, S is going to be connected, orientable surface, and I'll say without boundary. So if you haven't heard some, well, connected, I think intuitively makes sense what I mean by a connected space. Orientable is not that important. I just want to rule out some things. And without boundary is why I crossed out the picture up there. I don't want to consider things with boundary because when I start talking about mapping class groups, things get a little bit more complicated when you have boundary. I'm going to require the Euler characteristic of my surfaces to be negative. So it's not going to come up in the top, but the Euler characteristic is a number you associate to a surface, and when it's negative, you can put a hyperbolic structure on the surface. I do hyperbolic geometry, and so that's why I'm putting that restriction there. But for most of the talk, it's not even going to be relevant. Okay. So here's the first definition. So surfaces can come in one of two types. They're either finite type or infinite type. So S is said to be of finite type if it's homeomorphic to a compact surface with at most finitely many points removed. Okay, finitely many points removed, and otherwise it's of infinite type. Otherwise, infinite type. Okay, so that's a definition. That might not mean much to you. So just to quickly recap, homeomorphisms they preserve topological structure. So the official definition is that you have, two spaces, two topological spaces, and there's a homeomorphism between them. If there's a continuous map that's one-to-one and onto, and its inverse is continuous as well. But really what we mean is that it preserves topological structure. And so another equivalent definition that some people might like better is that surface is of finite type if its fundamental group is finitely generated, and it's of infinite type if it's not finitely generated. Okay, and if you don't like either of those definitions, that's the point of the pictures. Okay, so here are some examples of surfaces of finite type. So this is one. Here you have two donut holes. That's genus 2. Here I've drawn more donut holes. And then here in this surface where I have 3 donut holes, I've removed these 3 points, which I've marked by X's. And sometimes people draw this picture as the 3 points are made into cusps, and that's when I'm endowing this surface with a complete hyperbolic metric. You actually have these cusps that are sort of getting smaller as you approach the point. Okay, so I might draw pictures one of either way. Sometimes I'm drawing them just like this to make them look nice, okay, which is the case over here. So these are examples of finite type surfaces studied for a very, very long time, and they're classified by their genus. That's the number of donut holes, the number of boundary components, which for us we're not going to consider, so that's why I've left it off here. And then n is the number of punctures, the number of points that you remove. In fact, topologically, like you can just imagine taking a puncture and spreading it open. But when you're doing things like talking about mapping class groups, the distinction between a puncture and a boundary component is really important. Okay, so for us, finite type surfaces are going to have genus G and n punctures, and one or both of these be 0. Of course, with some restrictions if you want negative Euler characteristic. So now the fun starts. Most people don't spend their time thinking about infinite type surfaces, but now a lot of people are starting to. So some come up just whenever you're studying surface theory, like as covering spaces of our finite type ones. But here are some examples. They have some nice names. This one's called the Loch Ness Monster. Okay, I can draw it like a monster. I didn't do it here because I want the picture to look like the others. It just has infinite genus. That's why I've drawn the dot. And there's one sort of way of going off to infinity. Right? There's one direction in which the genus is going on and on and on. This is called the ladder surface. It also has infinite genus, but there's now 2 different ways of going off to infinity. Okay? This one is called the flute surface because you can play a flute here. And really what this is it's a sphere minus accountable collections of points that are actually accumulating, okay, onto, you're removing a sequence that's converging. But I've drawn them as punctures because it looks nice, okay? This we have now named the bi-infinite flute, okay? It looks like the flute surface, but instead of having just sort of the punctures accumulating in one direction, the punctures are now accumulating, the removed points are accumulating in 2 directions, okay? And then some more interesting examples. So there's nothing special about these surfaces in the sense that I can just puncture them in a few places. So I'm definitely going to want to think about, in particular, like this surface with one isolated puncture like that. It's going to come up later. You can draw that as a cusp too if you want, doesn't matter. This is a really interesting surface called the blooming cantor tree surface. So let me tell you what I've done here in case the picture looks confusing. I've taken a tree, an infinite tree, this one is valence 3, and I've thickened it and looked at its boundary, okay? And then I just punched donut holes everywhere, essentially. Okay, at every edge I've added in a donut hole. So it also has infinite genus. But it's very different than these two because there's way more ways of going off to infinity. In fact, there's a Cantor set's number of ways of going off to infinity because the boundary of every tree is a Cantor set. Okay, so this is just for people maybe who've seen more surface theory and have studied trees, but really you're starting to see that these are really big surfaces. Okay, that's kind of the point. And then you can take any finite type surface like our genus 3 surface, for instance, and just delete like a Cantor set. And that's also a perfectly fine surface of infinite type. Okay, so there is a group called the fundamental group. For all of these, it's finitely generated. For all of these, it is not. Okay, so that's just some examples to get you warmed up. And so what I'm going to be talking about today is the mapping class groups of these surfaces. The one thing I should say is that there is a classification for infinite type surfaces, and it's very useful. Whenever you're studying a class of objects, you really hope there's a classification. But it is more complicated than in the finite type setting. Okay, so if you're interested in that, I can tell you more about it later. Okay, so maybe one other thing I'll say is that, you know, of course, these are surfaces, and so you might think, okay, if people study those kind of surfaces, they should also study these kinds of surfaces too. But if you want additional motivation, these surfaces do come up a lot in certain areas, like in dynamics, in the theory of foliations of three manifolds, and in particular, the Loch Ness Monster comes up a lot in the theory of translation surfaces. Okay, so that's just some extra motivation because studying surfaces of infinite type is a newer thing, just to give you some motivation about why some people might be interested in those surfaces. Okay, any questions before I get to mapping class groups? Yes?
Do you consider non-orientable surfaces at all?
So you can, but I'm just ruling them out to make all the things that I say easier. Yeah, so obviously there are tons and tons of non-orientable surfaces as well, but I'm not going to talk about them. Okay, so, right, so let me define the mapping class group. Okay, so the mapping class group which will denote, let's say, I'll just do this, of S is defined to be the group of orientation preserving homeomorphisms of your surface up to some equivalence, which is isotopy. And that, again, it really doesn't matter if you don't know what that is today. So what I'm taking is all homeomorphisms of the surface. That means topological structure preserving maps of the surface to itself. And I'm going to make sure they're orientation preserving. And I mod out by some natural equivalence, and that's the group that I'm going to consider. Okay? So mapping class groups are considered as the group of symmetries of surfaces. Okay? And they're very, very important in low-dimensional topology. So they've been studied extensively, but really for finite type surfaces for the last 100 years or so. And you know, they're important to three-manifold theory, geometric group theory, the moduli space of Riemann surfaces, dynamics, it has lots of connections to dynamics. And like I said, most of the work that's been done on mapping class groups has been studied for finite type surfaces. So for the beginning of the talk, I'll recall some facts of the finite type surface land. But today we're going to go beyond that, and there's been this recent surge of people that are thinking about mapping class groups for infinite type surfaces. Okay, and a lot less is known in that setting. Okay, so part one, we're just going to talk about finite type surfaces. Okay, and so maybe I'll just start and give you some examples of homeomorphisms. Okay, so in case you've never seen this, let's say I take this genus 2 surface with two punctures, so that's S22. An example of a homeomorphism, so a map from S22 to itself, that happens to preserve topological structure is that you can just permute the two punctures. Okay? You just flip them, and that's actually in order to think, because like you, actually, okay, I shouldn't say that. Flip them. That's your mapping class, right? That's your homeomorphism. Here is another example, a very important one. So if I look at S, let it be this genus 3 surface. Okay, and I'm going to take a curve here. Let's just choose this one. This is my curve alpha. What I'm going to do is do a Dane twist about this curve. So that's denoted by T alpha. So what I do is I take, it's a very local phenomenon, a very local homeomorphism. It only occurs in this like little neighborhood essentially, all the change. So I take a little neighborhood of my curve, that's an annulus. Okay, so I'll draw it bigger just for demonstrating what's going on. Here's my core curve. This is the alpha curve that I'm going to twist around. So what I do here is I like basically cut this cylinder out, do a 2 pi rotation, and glue it back into the surface. Okay, so for a curve that was just, let's say, crossing through here like that, okay, after I do the 2 pi rotation, when I glue it back in, it's going to twist around here like that. Okay, so it twists and then I glue it back in. So it affects the surface quite a bit because it affects all curves that go through that region, right? But it's a very local effect. Okay, so this is called a Dane twist. And they're very important in the theory of mapping class groups because for finite type surfaces, there's a finite set of Dane twists that generates the entire mapping class group, okay? But I don't want you to be misled. These are like easy ones for me to tell you about. In general, homeomorphisms can be very, very complicated, okay? You're already starting to see that we're often concerned with, if you put curves on the surface, right, you draw closed loops on the surface and tighten them if you put a metric on them. You're concerned with what's happening when you apply this homeomorphism to the surface. How does a particular curve, maybe one that's going through this region, change under the homeomorphism, okay? And what happens if you keep applying the homeomorphism? What happens over time to that curve? So these are some of the things that, that people think about. Okay, so one of the really nice things is that though they can get very complicated, mapping classes, homeomorphisms of finite type surfaces, there is a classification of them as well, okay? So this is the Nielsen-Thurston classification. Of mapping classes. Okay, so if I take an element of the mapping class group, it comes in one of 3 different types, okay? The first one is that F is periodic. Okay, what this means is that if you take there's some K for which F to the K is the identity. Okay, so that's one type. That's a fairly simple type of mapping class. The second type is that F is reducible. So it's periodic, reducible. Okay, what does this mean? It means that F preserves some multi-curve. Okay, a multi-curve is a finite collection of a finite union of disjoint simple closed curves. So the curve I drew here, the purple one, that's a simple closed curve. Closed means it's a loop, simple means it doesn't intersect itself. Okay, so a multi-curve is a finite disjoint union of simple closed curves. So maybe I'll just if you take the purple curve there, and then this one, and this one, that's a multi-curve. It's three disjoint curves put together, okay? So a mapping class is called reducible if it preserves some multi-curve. So a great example of that is, for instance, a Dane twist about just one curve, right? It preserves that core curve. If I did a Dane twist about this one, and this one, that's also going to be reducible because it preserves those 3 curves, okay? So that's what it means to be reducible. They can be a bit more complicated than that, though. They're not just all solid Dane twists. The third type, and the most interesting type, is that the third type is pseudognoses. Okay, so there's lots of different things I can say here. I'm not going to give you an actual definition, but the way that you can think about pseudognoses is that F is highly mixing. Okay, maybe I'll say highly mixing all over the surface. That means that if you look at curves and how they act, how they change under the homeomorphism, they kind of go all over. Okay, and after iterates, they're all moving, mixing all over the surface. Okay, so it's really that this homeomorphism is happening everywhere at once. Some other ways that you can think about this, well, you can think about it as not periodic or reducible. All the rest of them fall into this category. And maybe a couple of other ways you can think about it is that no power fixes any simple closed curve. Any SCC is simple closed curve. And then the third way of thinking about it, which is like where the actual word Anosov and pseudo comes from, is that there's a pair of foliations, on the surface. And in one direction you stretch, and in the other direction, along one of the foliations you're stretching, and along the other foliation you're shrinking. But that's really just for people who really know something about this already. Okay, so already you're seeing from the amount that I've written that pseudonosovs are, of course, the most interesting mapping classes. They're very important as well. For instance, you know things in three-manifold theory about if you have a mapping torus and the map is a pseudonosov, you get a hyperbolic three-manifold. Okay, again, that's only if you know something about this area. But the other important thing is that they're ubiquitous. They're, in some sense, the generic types of mapping classes. Okay, I can say more about that, but that's not really the theme of the talk. So the most important thing that you're seeing here is that there is a classification. Okay. Yes. Yes. Okay. So this is a spoiler, but when I eventually talk about infinite type surfaces, one of the saddest things is that there currently is not a classification. Okay, and that's something that a lot of people are working towards. Okay. So one way of studying groups, and especially for studying the mapping class group, is via their actions on geometric spaces. Okay, that's the modern day view of how we think about groups. They act, right? They act on spaces. Okay, so for surfaces, we have something called the curve graph, or if you want to make it into a complex, the curve complex. And we gain a lot of information about the mapping class group via its action on the curve graph. Okay, so let me define that for you. So let S be a surface, the curve graph. And this you can define for finite or infinite type surfaces. There's nothing special about the type of surface I'm talking about. So this is denoted by C of S. Is a graph, and let me just tell you what the vertices are. The vertices correspond to isotopy classes. Ignore this word if you don't know what that means, but isotopy classes of simple closed curves. Okay, and you put an edge between vertices if you can find disjoint representatives. Okay, so if you have two vertices representing simple closed curves and they're disjoint on the surface, you put an edge between them. Okay, so this is disjointness. Okay, so I'm going to draw a little picture for you to help you understand what's going on here. So here's the example. So if I take, let's just say, this genus 3 surface, and I'll draw a few curves. So let's take this purple one. I'm messing up all the colors because I'm limited here, so hopefully I won't make a mistake. And then I have yellow somewhere. Okay, let's see. I don't know if you can see yellow. Like, does that look any different than white? Maybe. Okay, so here's the yellow curve. That's a vertex. The purple curve is a vertex. The green curve is a vertex. Okay? The thing is that these two are not disjoint. I don't put an edge between them. But the green curve is disjoint from the yellow curve, so I put an edge here. And the purple curve is disjoint from the yellow curve, and so I put an edge there. Okay? That's a really small piece of the curve graph. And I mean really small, because the curve graph is actually locally infinite. Okay, and it's infinite diameter. It's a huge graph. So that's just meant to highlight how you put in edges. Okay, it's a very, very small piece of the curve graph. Okay, I can make this graph into a metric space just by assigning each edge length 1, okay, the graph metric. And it's a particularly nice and very important graph. You study type Miller space and mapping class groups often in connection to the curve graph. And one of the nicest theorems, I think, about the curve complex is due to Mazur and Minsky. And what they proved is that this graph is an infinite diameter graph. And it's also delta hyperbolic. An infinite diameter delta hyperbolic graph. Okay, so infinite diameter means what you think it means. Okay. What does delta hyperbolicity mean? So I'm not going to harp on this for too long, but I'm going to draw you a picture. So a space is delta hyperbolic if triangles are delta thin. Okay, so if you pick points in space and you connect them up by geodesics, so locally length minimizing paths, then the triangles look thin as they do in hyperbolic space. Okay, so what I mean here is if I take 3 points in the curve graph and I draw this triangle, okay, then the official definition is that if I take a delta neighborhood of both sides, so this is a little delta neighborhood of two sides of the triangle, so this one and this one, okay, that it's going to encompass the third side. Okay, the union of these two delta neighborhoods encompasses that third side. And that's going to happen when your triangles tend to like sink in towards the middle, right, when they're thin. This is a phenomenon that happens in hyperbolic space, and so you call it your delta hyperbolic if there exists some delta, so that you can do this for any triangle in this space. Okay, for any triangle you give me, it's delta thin for that delta. Then I call this space delta hyperbolic. Okay? So the infinite diameter criteria is interesting and important for when you study the dynamics of the mapping class group, for instance, acting on the curve complex, the curve graph. I might say complex. I'm only thinking about vertices and edges. You can fill in higher things, though. That's why I might mess that up. This notion of delta hyperbolicity was introduced by Gromov in the 80s for studying, well, first for generalizing hyperbolic space, but also for studying groups in a geometric way. So you say that a group is delta hyperbolic if its Cayley graph for some generating set is delta hyperbolic, so triangles are thin. Maybe one thing I'll say is that it turns out that the mapping class group, you can never put down a generating set so that its Cayley graph is going to be delta hyperbolic. So it's not a hyperbolic group, but we can gain a lot of insight by understanding its action on a hyperbolic space, like the curve graph. Okay, then you can maybe use some tools from hyperbolic geometry to study the mapping class group and gain algebraic and geometric information about it. Okay? So maybe one thing I'll just write down here is that the mapping class group acts on the curve graph via isometries. Okay, so that's the first part. What I mean here is that you have this graph. It consists of simple closed curves and their relationship to each other. So a mapping class group element is going to take your surface and map it to itself. So it's going to send these curves to other curves of the same type. So simple closed curves go to other simple closed curves. So it's changing the graph. Okay, it's acting by an isometry on the graph. The really important thing is that, and I'll put this in a little box up here, F, an element of the mapping class group, is pseudo-Anosov if and only if the action of this particular element on the curve graph is loxodromic. Okay, this is the really important thing. So what I'm saying here is that the action of the mapping class group on the curve complex actually gives some sort of classification, a coarser classification of the elements. And the most interesting type of dynamical action that you can have comes from these most interesting mapping classes. Okay, so maybe I'll squeeze in a little picture in case you haven't seen this. So loxodromics are kind of like they act like hyperbolic isometries do on hyperbolics, loxodromic isometries do. So the idea here is that I'm drawing the curve graph as like this little ball, okay? And what's going on is that F is going to fix some sort of axis, infinite axis, bi-infinite axis in the curve graph, and it's going to act on that axis by translation, okay? So I have some, and this is a schematic for drawing a piece of the curve graph, but you have this axis, okay, and F is acting by translation. It's moving things along. So there's a source sink sort of phenomenon going on, just as you have, if you've seen this, in hyperbolic 2 space when you're looking at loxodromic isometries, okay? So this interesting dynamical action. Okay, if you don't want to think about that, just when you see this word, it's good. Okay, that's a good action. This is an interesting action. Okay, so loxodromic actions are good. And pseudonosovs give it to us. Okay, so that is all the stuff I want to tell you about finite type surfaces and their mapping class groups and the curve graph. And now I'm going to move into the infinite type setting. So are there any questions before I do that? Yes? Can you speak up a little bit? Explain this again? Yeah, sure. So I'm saying that if you have a pseudonosov element of the mapping class group, so it falls into this third type, then in the curve graph, which I've just drawn as a ball here, it's obviously not a ball, okay? But it's some huge infinite diameter thing. And there's some axis, it's actually a quasi-axis, for quasi-geodesic axis, for those people who know what that means. But it's some axis, a bi-infinite path in the curve graph. And F is actually acting by moving along that axis. So it's taking a simple closed curve alpha to, this is F of alpha. And then if I keep going, I get F squared of alpha. So as I keep applying that homeomorphism, I'm translating along the axis. So there's this source sink dynamics where it looks like it's coming from here. This is the source, and the sink is over here. Okay? Okay, any other questions? Yeah.
What kind of hyperbolic space that define the circle
Yeah.
always have to do that.
Yeah, so it's important here that I'm talking about like some infinite diameter space, right? And that there's actually a notion of like a boundary and stuff, and I'm really looking at like 2 points in the boundary, and of course I'm talking about geodesics. So make sure it's like a metric space so you can measure things and say, oh, this is delta hyperbolic. It's important that I put a metric on the space. But then once you have an action, you can ask if it's loxodromic, right? So like, is there some quasi-geodesic axis that this element is acting like by translation?
There's a lot of parameters. Is it that the only parameter besides the hyperbolic?
I think if you can talk about geodesics and quasi-geodesics and there's bi-infinite paths like that, I think you're good. Yeah. Okay. So, let's see. Yes. I'm going to erase some of the pictures here. Okay, so for these surfaces now, the infinite type ones, the mapping class group is defined in the same exact way. Okay, it's a group of orientation preserving, so this is part 2, infinite type. Okay, so the mapping class group is defined in the same way, and these are called big mapping class groups. So if you've seen that word pop up, people are talking about the mapping class groups of infinite type surfaces. Okay, and these groups are actually very big. Okay, they're much bigger than finite type mapping class groups. Those are finitely generated. These are not. Okay, so that's one reason why the geometric group theorist starts getting a little scared, because we definitely rely on finitely generated to talk about a lot of things. But plenty of geometric group theorists are now studying this. Okay, so it's just to caution you that things get messy for sure. The thing I should tell you about these is that again they arise naturally in the theory of dynamics. Okay, that arise in dynamics. Foliations of three manifolds. in something called the artinization of groups. I'm not going to say much about that, but I can tell you later if you'd like. And they contain interesting groups as well. For instance, if you take the sphere minus the Cantor set, and you look at its mapping class group, it contains one of the Thompson's groups. Okay, so a lot of different elements are going into the theory of big mapping class groups. I mean, there's some results that borrow from like descriptive set theory that I would have probably never looked at until I started working on these kinds of things. Okay, so it's really growing, and I think it's a really exciting place to be working. Okay, so if you're interested in sort of an intro to big mapping class groups, there's a few papers that I can direct you to, but there's also these 2 blog posts by Danny Caligari that he wrote about big mapping class groups, and they're really great, so I would suggest reading them. I would suggest everybody reads them, okay? So that's your homework for the weekend. Okay, so of course there's the caution that I gave you before, which is that there's currently, and I'll say that because there may be, if one of you does this, for instance, there's currently no classification. So no Nielsen-Thurston type classification for mapping classes of infinite type, and the situation is more complicated and more delicate, but I think that's what makes this kind of exciting, right? So what is the right definition for pseudo-null sub in this setting? We don't know, okay? There's a suggestion that's been made, and I think it's pretty good, but it's not clear if that's the right answer yet. Okay. So there is another piece of bad news before I get to better things. Okay, so more bad news. In this setting, for infinite type surfaces, the curve graph is finite diameter. In fact, it has diameter too. So the way that you see that is, let's draw one of our favorite surfaces. This one. Okay, the ladder surface. And if I take some complicated curves here, I don't know, something like this curve. Okay, that's a perfectly fine, simple closed curve. And maybe I look at, something going like this. And it'll go around the back and connect up to itself. Okay, those are complicated, they intersect each other. Maybe you think that their curve graph distance is high because that's measuring disjointness. But in fact, I can very easily just draw always a third curve over here that's disjoint from both of these. So that makes this distance 2 again, okay? In this case, I only drew a tiny piece. There's since I said it's infinite diameter, I can draw really complicated curves on finite type surfaces where you really need to go to there's a long path between them in the curve graph. So you can't just go to some mutually disjoint curve. Here, no matter how complicated I make these 2 curves, okay, the purple one and the yellow one, there's always some green curve that's disjoint from them. Okay, the way you can see this is that there's lots of room in this surface, right? It's just huge. These 2 are compact, they're closed curves, so they're going to lie in some compact piece of the surface. You just look at the complement and choose some curve far out in the surface. So this is pretty bad. I mean, you can still study the curve graph. It's just that you're not going to really understand the algebra and geometry of the mapping class group via its action on a finite diameter thing, for instance, right? You're not going to be able to talk about loxodromic isometries versus elliptic ones and parabolic ones. So this is not good. But the question then is that, so is there some good infinite diameter delta hyperbolic graph that mapping class groups of infinite type surfaces act on? So is there some other infinite diameter delta hyperbolic graph associated to S? Okay, and I think you would know that the talk would be over if there wasn't something that you could do. So thankfully there is another graph that I can think about. There's actually a few. A lot of people are actually working currently on coming up with as many possible good graphs that are infinite diameter and delta hyperbolic for these kinds of surfaces to act on. Now, one caution I'll give is that there's not like a catch-all. Like in this case, all surfaces have a really nice graph. It's the curve graph. That's what you use. For infinite type surfaces, depending on which picture you're looking at, you might have to pick a different graph. Okay, so today I'm going to basically, for the rest of the talk, always assume that I have one isolated puncture, at least, in all of the surfaces that I'm going to talk about. Okay? So here's a definition for the relative arc graph. That's going to be our saving grace here. So let S be an infinite type surface. Okay? With at least one isolated puncture. Don't worry about the word isolated, it just has a puncture. Okay, an isolated puncture, P. Okay, so I'm going to define this arc graph relative to P be the relative arc graph. And how is it defined? Okay, vertices here are going to be arcs that are still simple, but they start and end on that puncture. Okay, so isotropy classes of simple arcs, beginning and ending at P, the puncture. Okay, and again, as usual, edges denote are put between two vertices when you have disjoint representatives. So that's never going to change. Okay, disjointness is going to be when you add edges. So let's look at, again, a little picture. This is, again, a very small piece of this graph. So now I'm going to just put maybe my isolated puncture right there. And I'm just going to look at arcs that look like this. Okay, this one. Maybe I have something that looks like this. Okay. And those are my arcs. Again, I can draw when they're disjoint. So let's see, the purple and the yellow are disjoint from the green. Okay, so I have something like that's some small piece of the relative arc graph. Okay? What's that? Ah, yeah, it totally does. So yellow is mutually, yeah, this is the right way. Thanks, Dave. So, did I just do that right? Yeah. So yellow is definitely disjoint from both of them. That's what I meant. Thank you. Okay. Yes?
So the puncture is not in the surface, right?
The puncture is technically not in the surface.
So I'm confused how we got past. So
Yeah, so there's this thing that topologists do where we blur the distinction between like a puncture and a mark point. It's just like a special point that I'm putting down. And what you can think of is that if I draw this as a cusp, it's just like arcs that are running out of the cusp. And they start coming out of it and then they go back. But it's much better to think about it as just some mark point.
yeah,
that you're
that's
starting.
good.
Yeah. But it is important sometimes because it's important that it's not in the surface for other reasons, okay? Okay, so there is a really nice theorem. This is due to Aramayona, Posas, and Collier. Just from a couple of years ago. Okay, and they proved that this graph has the properties that we want. Okay, so this is now an infinite diameter delta hyperbolic graph. Which is awesome because now I'm going to start asking the right questions, right? You know, the mapping class group, some sort of mapping class group is going to act on this, and then I'm going to ask about, you know, what are some interesting actions? Are there some loxodromics? What are they? Where do they come from? And so on. Okay, so that's their theorem. And the one thing I have to be careful of is that if I have more than one puncture, like we saw for this example, punctures can be permuted, right? So if I actually had this surface with like 2 punctures, I don't really want to be looking at mapping classes that permute them because I'm looking at only arcs that start and end on this one. It's a very special one. I want to keep it fixed. So obviously in this case, the full mapping class group is going to act on this arc graph. But if you have more than one isolated puncture, you have to be looking at a subgroup of the mapping class group. So let me just write that down. So if we let map of SP, okay, this is going to be the mapping classes that fix this particular point that I'm interested in. Okay, so be the subgroup that fixes P. Okay, then the mapping, this group acts on this relative arc graph, again, via isometries, in the same way as before. Okay, and when there's just one isolated puncture, this is the full mapping class group. Okay, but I can put in some more. It's perfectly fine. Okay, so here's the question: what are the loxodromics, right? Isometries of this arc graph coming from this action. Okay, so there are some that are coming from finite type theory. Okay, so in this same paper, what this group of authors shows is that if you have, let's say, this surface, and I look at some, I cut this off and I look at this surface, S prime, okay? And if I take that finite type subsurface and I take some pseudo-NASA on that, okay, some highly mixing homeomorphism that doesn't do anything on the rest of the surface. In this paper, what they show is that those actually do act loxodromically on this arc graph, on this relative arc graph. But of course, those are not the most interesting ones when you're trying to study finite type surfaces, right? You want to talk about maybe some intrinsically infinite type homeomorphisms and show if maybe there are some that are loxodromic. So maybe I'll just write down, since I do have a bit of time, I'll say that these three authors are Mayona, Posas, Carlier, show that pseudo-NASA on S prime in S, which is a finite type surface, finite type subsurface, these are loxodromic. But what else, right? That's the real question. What else? It has to contain the isolated puncture. Yeah, definitely has to contain the puncture. Okay, and now the question is, really, are there any mapping classes that are acting on this of intrinsically infinite type that are acting? Oh yeah, do you have a question? Yeah.
Because I think there will be some arc that we can go far away is going from.
This is, okay. Well, you have to be careful. So it's not like completely obvious like why this is first of all infinite diameter. You really have to convince yourself. There are arcs that this puncture being here and all the arcs starting and ending on that is very important. Because if you start looking at arcs that kind of encapsulate the puncture, then all of a sudden it's really hard for things to be disjoint from that. Okay, without being sufficiently complicated themselves. So I can't draw those by hand, but maybe I can show you some on the computer if it works, which it might not, in a second. Okay, but yeah, it's not totally obvious. Okay, so now the question is, instead of just are there loxodromic isometries, are there intrinsically infinite type loxodromics? What I mean by that, by intrinsically infinite type, is not supported on some finite type subsurface and not the limit of things that are supported on finite type subsurfaces. If you don't know what that means, it's okay. But in some sense that, are going sort of, the homeomorphism is applied all over the surface, okay, or at least on a big infinite part of the surface. Okay, well, if you're asking are there any intrinsically infinite type loxodromics, should first ask, are there any intrinsically infinite type homeomorphisms at all? Okay, we haven't really addressed that question. So the first question is really, are there any elements of this relative mapping class group that are intrinsically infinite type? Okay, so I'm going to try to make the computer work, and if that fails, we're just going to go by hand. Is there a relationship between ASP and?
I don't know this answer, but that's the question that's big, yes.
There's not really, in the sense that there's nothing, all the fundamental groups of infinite type surfaces are the same. They're infinitely generated free groups. Okay, so yeah, there's not going to be like some sort of interesting thing I can say there. Yeah.
Whatever you add, but like, you do crazy things for the free group that you probably can't do out of left.
That's right. Okay, yeah, go ahead.
I think you mentioned first definition of pseudo-non-stop. What definition of pseudo-non-stop is this pseudo-non-stop? Show pseudo-non-stop.
Oh, so I'm talking about pseudo-non-stop on a finite type surface. So all those definitions I gave were all equivalent for the finite type in the beginning of the talk. I'm so happy that this is working. Okay, so any other questions before I show you some pictures? Okay, so first question. Are there any infinite type elements of the mapping class group? The answer is yes. What they are handle shifts or generalized handle shifts. Okay, so what is a handle shift? So here I'm actually drawing this surface just differently. What I've done is taken the genus and pulled out each of the handles. Okay, so this is still, and of course that thing is actually like, it has a back, that's a cylinder, right? That strip is actually a cylinder. Okay? What's that?
This is not intrinsic, right?
I'm saying that this is an infinite type homeomorphism. Because if you look at the support, it's on almost the whole surface, right? So what I'm doing is I'm saying that the red part is the domain of the handle shift. And what it's doing is just moving all the handles in the domain over by one. Notice that I've drawn it to skip the puncture and skip that 0th handle that I can draw there. It's definitely shifting like -2 handle to -1, -1 handle to 1, the first handle to the second, and so on, okay? But it's skipping some, okay? And I can draw, this is just an example of a handle shift, okay? So I pulled out all the handles and I'm just moving over, okay? That I'm gonna claim is like an intrinsically infinite type homeomorphism that doesn't come from finite. We can't actually, and we can prove, this is in a paper by myself and Nick Lennon, you can prove that it's not the limit of finite type homeomorphisms, okay? So here is what this does to, let's say, one of these arcs, like that I've drawn. There's the puncture, there's a blue arc starting and ending on the puncture, and here's one iterate. It's moving over that genus, right? It's moving over that handle, so it's looped around -1 instead of -2 now. And now comes the interesting part. If I apply the homeomorphism again, it's gonna sort of swing around that genus 0, right, the 0th handle, and move past it. And now you're seeing that there's some actual interesting stuff going on because I've skipped that genus in my support of my handle shift. Okay, there's a little bit of bad news. These are not loxodromics. Okay, they're not loxodromics. They're just not complicated enough. And I won't say more about that since I'm kind of running low on time. What you can do though is a little bit of a I mean, you can, instead of just looking at one handle shift, you can look at a few of them and put them all together. And I'm going to claim that that's sufficiently complicated. So here's the theorem with Carolyn Abbott. Oh, I spelled that wrong. It's A-B-B-O-T-T. And Nick Miller. So for most infinite type surfaces, there's an infinite family of infinite type elements that are loxodromic isometries. Okay, so you give me a surface with some conditions, I can produce an infinite family, we can produce an infinite family of elements that are acting loxodromically on this arc graph, okay? So really quickly, I can show you kind of what we've done. The first step, if you don't want to think about it, just ignore it. But what you're really doing is take your handles and just like chop them off. Okay, so now I'm looking at like some cylinder with a bunch of boundary components and a puncture. And as long as you can embed that into your surface, we're good to go. That's when I say most infinite type surfaces, okay? So that's step one. And so what I'm really gonna do is produce a very interesting homeomorphism of this surface, and that's gonna sit inside of my big surface, okay? So I've just chopped the handles off is what you then thought about. If you wanna keep them there in your imagination, go for it. So here is how we build one of our homeomorphisms. It's the composition of 3 handle shifts. Here are their domains. Okay, the first one is the one I showed you. The second one is doing a weaving, and the third one skips over some of the handles, right, the boundary components, and then under the puncture. And what is actually going on, this is just one example, and then the other, the infinite family, is a generalization of this composition of 3. So you can do compositions of 3 different ones in many different ways and get loptogenomics every time. So what's going on is that you apply one of these in the right shift, you do the second one in the left shift, the third one you do right shift. And what happens is that you start getting some mixing. It's mixing up a lot of things in this turbulent region in the middle. Because you have sufficient weaving, I'll get to your question in just a second. Because you have sufficient weaving, you start to see your arcs getting very complicated very quickly. Okay, question? What's that? Oh, I definitely don't know how to do that, and I'm very scared. So I only have like 30 seconds left, so I'll turn it off maybe after. Okay, so I'm just going to show you what some iterates of a curve look like. So my claim is that this is a loxodromic. So in the arc graph, I should be able to find some sort of axis and show that this F is actually mapping along. So the first curve I'm going to take, that's my alpha 0. And now I'm going to look at iterates of it and see what's happening. Okay, so the forward axis, for instance. So here's the first one. And then things start to go way more complicated. This is a train track version. Thanks, Dave. This is a train track version of the second curve. Because the second curve is actually so difficult to draw that it like takes me an hour to do it properly. Okay? So that the weights on there is actually telling you, and I know it's blurry, but the weights are telling you the number of strands. Okay? And then if you do the kth iterate, this is kind of what the train track looks like. So you'll see that the curve is starting to go all over the surface. And really importantly, let's see if I can, I don't know what this is. Oh, there we go. So in this region, this looping, it increases very, very quickly. The number of strands that are going around the puncture is going very high very quickly. And so if you're looking at arcs that are disjoint from this, they're very complicated, and they actually have to like sort of fellow travel your curve for a really long time. Okay, so this is just to show you some of the pictures of like iterating a curve under this homeomorphism, so you start to see we have to prove things about the way that these curves intersect and what their arc graph distance is. And we can show that the arc graph distance is getting really big if you compare alpha naught to like alpha k. Okay, it's going off to infinity. I don't have a thank you slide because I just like fixed these up, but thanks.
Any questions for us?
You choose who does.
We can just start from this way and go up.
Yeah, so what changes in your fluid communication when fluid surfaces? You're looking at kind of different.
Yeah, nothing, basically. So the fluid surface, what you're doing is you're saying, when I want to take, remember this surface that I have? As long as I can take this surface and put it into my surface, I'm good. So in the fluid surface, I'm just chopping off all the fluids. As long as I have an isolated puncture, I can just put this right in. And the complementary region, so there, your complementary region is like some sort of cone thing, where before it was a handle. As long as you have infinitely many of the same complementary region, you can do this. And they can be really complicated. Okay, they could be like one big branch of like a cancer tree surface. As long as you can put that on everything and then just shift, you're good. Yeah.
So we have a picture of the example that's showing this arc graph has infinite diameter.
Oh, yeah, so I don't have those pictures on the slides. I mean, you can kind of see it. It's this, I was really hinting at this train track picture. So like getting curves that are disjoint from this here is quite difficult. I haven't drawn like, oh, here there are numbers. So the number up there is just 4. Okay, that's just a 4. But in the next example, this number is really, really high. So like if I just go to alpha 3, this number is going to like 48 really quickly, and then it's growing and growing and growing. So in order for a curve, an arc, to start here and end here, it has to sort of start following along, because it's trapped in lanes.
It's a finite number,
It's a finite number.
so it should be,
Yeah, it's not easy to see. I mean, I'm not claiming that there's not like some sequence of curves that's like, this is maybe disjoint from, so if the real question is if I draw this and some other complicated arc that's intersecting it a lot, I'm claiming to you that you have to go through a sequence of pretty long arcs in order to get them to be connected by disjoint arcs. That's the point.
there's the exist right now, because
I don't think it's clear that you can escape this in a very convenient way. We should talk about it after. It's very delicate. You don't have to be convinced. I didn't do a good job convincing you, but I can with time. Yeah. Okay.
So in terms of the applications
Yes.
of big math class groups, I know that ordinary math class groups, one of the reasons they're studying is sort of like decomposition of closed three manifolds and how things connect up. Does the same thing apply, and what class of three manifolds does it
Yeah,
apply to?
it's not clear. So I'll honestly tell you that it's only been a few years that people have been really like jazzed on big mapping class groups. So going towards like three manifold questions, like an example is, if you give me this homeomorphism, it looks like a loxodromic. So maybe it has some like pseudo-Nosov type properties. Let's make a mapping torus. Is it hyperbolic? We don't know. We don't know anything. Okay, so those questions are totally wide open. So I don't know of any sort of applications in that direction yet, but I think they're really interesting. Yeah.
So something that makes me really sad about like out of the the fundamental group is that like you could just permute the generators, and that gives you like a symmetric group on infinitely many things. You can get too many groups there. Is there like an abstraction in this case from like getting some sort of like infinite permutation group?
I don't know, but I don't think so. But I don't think I understand your question.
Right. So like something that makes me sad as a geometric group theory is if I see like the permutation group of infinitely many things, that tells me I see every countable group in a subgroup all at once.
Oh, I see.
And
Yeah,
I don't want that.
Yeah. So the question of what groups are arising as subgroups of mapping class groups, big mapping class groups, is again completely open. So there are examples where I can show you that certain countable groups cannot sit inside of mapping class groups, certain mapping class groups. Yeah. So we should talk about that. There is some interesting things going on. Yeah. There's very interesting groups that do sit inside, and then there's some examples that don't sit inside, and a lot of the typical things for finite type surfaces algebraically for their mapping class groups is just not true. Like for instance, these are not even residually finite. The full mapping class group for an infinite type surface is never residually finite. That is like a basic group property that we all want, right? And they're not. But yeah, that's just, so for instance, some residually finite group, okay, it can sit inside, but that just shows you that the algebraic structure is really different.
You want reducibles to fix stuff.
Yeah, but I don't know if that's the question. The question is why don't we put edges when things intersect? That things intersect often is maybe part of the problem. Like you want to, okay, maybe I'll say this. Let's say you're talking about two curves on a finite type surface. If you make a graph that's like, oh, just put an edge when they intersect, well, it's not capturing how they intersect and how much they intersect. And the curve graph can do that. Because if they're intersecting a lot and going maybe all over the surface, then their curve graph distance is very high. So if you just say, put an edge if they're overlapping, then two really simple closed curves that I can just draw in a second with one intersection, would be distance 1, but a pair of filling curves would also be distance 1, and that's not really giving me insight into the surface theory.
So what is the relation between like a curve complex and a curve graph and a graph where I believe the edges might accomplish the intersection?
Oh, I don't know. I have never thought about that. I don't know, maybe some people have thought about that. I guess.
So, injection, so, someone Priya studied so, you build a sequence of graphs, where you put an edge between pairs of curves that intersect the curves of k times, and these turn out to all be delta hyperbolic functions graphs. It's studied, but generally bounding intersection, because once you have a pair of curves that intersect, you can build curves that intersect a whole lot.
That's a little bit different than weighting the edges. I don't know about if people have studied weighting the edges. Yeah. That's, what's that? Of the same spirit, yeah, definitely of the same spirit, yeah.
Okay. Any other questions?
You said early on that you weren't exactly sure how to define pseudo-Gnostic maps for different type
Yeah.
surfaces, but there's ways to work on it.
Yeah,
What's the current guess? What do you
Yeah.
expect, and how's it different from the stretching and shrinking of
Yeah.
finite surface types?
so I think that probably the guess is that you should call something irreducible. So maybe calling it pseudo-Gnostic is like using some theory about foliations and stuff like that. Well, let's just say irreducibles. Probably it should be that it fixes no multi-curve period. It could be a finite or infinite multi-curve. Okay, and the infinite multi-curve gets you to understand why the handle shift is reducible. Okay, so that's just something to maybe think about. Okay, so. Yeah, but let's just say that there was an AIM workshop that I was running with a few people just like last 2 months, a month and a half ago, and that was one of the biggest questions. And like, we don't know, even if you put down that definition, is there some sort of way of classifying loxodromics? Because, you know, are the ones coming from this type of construction versus limits of pseudo-Gnossos, you know, how are they the same or different? Like in one, do you actually see some sort of foliation, and maybe in another you don't? But this is kind of nice because you're seeing some train track action, right?
Yeah.
And that's like, it's looking like it has a lot of the flavor of a finite type pseudo-Gnosso. So yeah, it's, again, like so many questions and like, so, yeah.
So in other words, you found things that are really similar in flavor to what your body surface looks like the right areas.
That's right.
Okay.
So answering the, I mean, you know, what would we love for this paper to actually do is like, what are all loxodromic elements?
Yeah.
That's just fantastically hard. So instead, you know, we're at the stage now where we're just trying to come up with families of examples, and we have, this is one construction, and there's a construction of Ferran Valdez and his student, Israel Morales, and they have a completely different, that's coming from like a Thurston type construction of taking two multi-curves and doing a simultaneous twist around two of them. And there they've produced, again, another loxodromic. And those look like limits of pseudo-Gnossos.
Yeah.
So are those all of them? And can you give some criteria on, let's say, 2 or 3 handle shifts, probably 3, where you definitely always get this kind of enough mixing, right? That's another question that I think is like super relevant. Yeah.
Gotcha.